So at this moment, we're going to go ahead and find the critical points and the inflection points. We have two types of critical points. One is the x's that make the y prime 0, and the other one is the x's that make the y prime undefined. So we can do the undefined part pretty quick here because we know from the previous step that x equals -9 and 9 would make the bottom of the function 0, so the function is going to blow up at those points. For finding critical points that make y prime 0, we're going to set the top 0. There we go. X, well, why don't we factor x squared out? X squared minus 243 equals 0. So this implies that you have x equals 0 and the roots of x squared minus 243 equals 0. And you can check that. You have x equals plus minus 9 roots 3. In turn, you have 5 critical points. Similarly, we're collecting the points that makes the bottom of y double prime 0. So these are like -9 and 9, as well as the x's that make y double prime 0. And these are the x's that make the top 0. Well, this quantity is positive, so there's no way you can get anything out of this. But this x equals 0 is making the top 0. So in turn, you have 3 inflection points and 5 critical points. All right, it's time for bringing everything together. So we had the critical points and the inflection points listed here all the way. And what we do is we look for sample points from each sub-interval and then evaluate f prime and f double prime at those sample points. So at this moment, have your calculator ready and try to evaluate, let's say, f prime at -20, f prime at -10, all the way to f prime at 20, and determine the signs of each output. And do the same thing for f double prime. So you have the expression of f double prime from the previous step, and go ahead and then punch in those numbers, sample points. And your sample points could be totally different from mine, so don't worry about it. So choose your own sample points if you wish to. You get plus here, so the function is increasing because of the test for increasing and decreasing behavior. So decreasing, 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 and decreasing all the way. But since this sign is plus, it turns back up and increasing here. So looking at the sign of f double prime, we can use the test for concavity. So f should be concave down here, concave down, up, down because of the minus sign, up again, and up again. All right? So in the last final step, you bring these two rows together and you determine the exact shape of the function. So for example, you have an increasing function but concave down. So you get the increasing portion of the concave down graph, right? Because concave down has like 2 pieces, right? So one is increasing and the other one is decreasing. So we got the increasing part. And in fact, in the next column here, we have decreasing and concave down, and we collect the right piece of the concave down graph. And you do it for all of them and get the description of the function like this. So the ultimate goal here is to determine the inflection points and relative extrema. So as you see that you have concave down and increasing and decreasing, so you should probably have a relative maximum value here. And from here to here, well, it's decreasing, but it keeps decreasing all the way. So it's just inflection point, but nothing for relative extrema. And then here, it's decreasing. Well, it keeps decreasing, even though the concavity changes, it keeps decreasing. So no relative extrema except the inflection point here. And then same type of behavior, it's decreasing and decreasing, but the concavity changes, so you have another inflection point here. So from here to here, we have a relative minimum value here because it keeps decreasing, and all of a sudden it changes the behavior and it keeps increasing, so we have a relative minimum value. So here's the outlook of the graph of the function. You can go ahead, in fact, and graph this whole thing with your hand, because we know the vertical asymptotes. Here we go. There's one right here, x equals -9. X equals 9 is another asymptote here. We know the x and y intercept, so the graph is gonna cross the origin here. we have a slanted asymptote y equals x line. Here we go. And you can just like copy all the function graphs and paste them all here. So for example, I know the graph of the function at this moment. And in fact, we have the limit behaviors also found in the previous step, right? So we have no horizontal asymptote. In fact, when x approaches minus infinity, so the function values would approach minus infinity. So we know that the graph is going to come from minus infinity all the way up to the point -9 √3. Here we go. Let's check. It's coming through the slanted asymptote because, again, we don't have a horizontal asymptote. It goes all the way up to this point, which is -9 √3. And it stops over there. It makes a maximum. And then it goes back down. All the way to where? Well, probably all the way to the asymptote. We have a vertical asymptote at x equals 9. So we check the limit as x approaches -9 from the left. And we found out that it's minus infinity. So it's going to go to minus infinity with that shape. Let's go back again. Here's the shape of the function, right? It's concave down, but decreasing. Here we go. I have concave down and decreasing all the way. So we need the limit of the function on the right of -9, and we found that it's infinity plus infinity. So let's check what kind of function we have here. So here we go. We have this kind of like concave up, decreasing type function. Here we go. I have concave up, decreasing, but it's decreasing from plus infinity all the way to my x and y intercepts, which is the origin. And then after 0, the behavior of the function is concave down, decreasing. But then we're going to hit another vertical asymptote here, which is x equals 9. So starting from here, you put decreasing concave down, and we check the limit on the left of the point x equals 9. And it was -infinity, so this function is going to decrease all the way to -infinity. And also we check the limit of the function on the right of x equals 9. Okay, that was plus infinity, so we're going to come from plus infinity. With what shape? Let's check from the graph here. It's going to be concave up, decreasing. Here we go. I have concave up and decreasing all the way to the next point in the table, which is 9 √3. And I have a relative minimum here. So I'm going to increase all the way to infinity along y equals x line. Okay, so let's check the behavior again. It's going to increase concave up all the way along the asymptote, the slanted asymptote, which is y equals x. So I sort of like graph this by using a software, but I want you to graph this by hand, by yourself, as the way I explained. So why don't you just graph, copy paste all the concave down up behaviors together with the increasing decreasing behavior. So just copy that information, paste it down here together with your relative extrema, intercepts, asymptotes, and also the relative extrema. All right, so this was a long video because we had a lot to check in the list, including the slanted asymptote. Don't forget that we do long division to find slanted asymptotes, at least for the rational functions of this kind of expression here. And you check all the limits on the left and the right of the vertical asymptotes. You find relative extrema and inflection points. And you match your findings with the graph of the function that you can use a calculator or a software. All right, thanks for watching. I'll see you in another video. Bye.